Thanks to the wide availability of cameras and to the large adoption of photo sharing applications such as Flickr, there has been a marked increase in the amount of publicly accessible user-generated photos. People are capturing and sharing their experiences, ranging from visiting sites of tourist interest to participating in events such as concerts and conferences. As more users share their pictorial content, more and more objects and events of the real world are captured and made available through social media. Within the massive amounts of user-generated data, there are extremely interesting bits of knowledge and content. However, the lack of structure and the sheer magnitude of such content make it extremely challenging to find the underlying information treasures. If we could browse through the whole set of photos that users share through social media applications, we could get many interesting insights into how people experience the world. Through users' photos, we could discover what the people see, what they do, and what they like. In order to tap into this great potential of social media, we are in need of new tools for content organization and exploration. Image clustering is a promising tool for achieving this goal. Photo clusters can be seen as convenient units of organization, and frequently they can be associated with real-world objects and events. Furthermore, thanks to the availability of geotagging information with respect to photos, we can identify the cluster's geographical position and thus project them on a map. This is the basic idea of our proposal, a content analysis framework that enables the organization of large amounts of user-generated content into photo clusters that are associated with real-world landmarks and events. Our starting point is a set of photos that are described by tags and that are associated with GPS coordinates. This is how the proposed system works. We first create a graph that represents the similarities between photos in terms of both visual characteristics and their tags. Then, we perform an efficient graph clustering scheme in order to extract clusters of photos that depict the same real-world entity. Subsequently, we derived a feature description for each cluster in order to automatically classify it into a landmark or event. Finally, we post-process the clusters that have been classified as landmarks in order to refine them and label them automatically. In our first step, we create a hybrid photo-similarity graph, that is, a graph containing the photos as nodes and their pairwise similarities as edges. We exploit two kinds of similarities between photos. First, we take advantage of the fact that users describe their photos by means of tags. When two photos are described by similar tags, we insert a tag similarity link between them on the graph. There are several measures of tag similarity that one can use. For instance, one could use the co-occurrence of tags across photos. This is a simple and computationally efficient option. Alternatively, for more precise results, one may turn to more sophisticated tag association measures, for example based on latent semantic indexing of the tag space. In addition to tag similarity, we also take into account the visual similarity between images. Starting from a feature-based representation of photos, we compute pairwise distances between them and then insert visual similarity links on the graph between each image and the 20 most similar photos in the dataset. As visual features, we make use of SIFT descriptors and a bag of words model. Alternatively, it is possible to use other kinds of visual descriptors, such as SERF. The second step in our analysis involves the extraction of clusters of similar photos by use of an efficient graph-based clustering scheme. The employed method is based on a simple principle. Find subgraphs in the photosimilarity graph that are more densely connected to each other than to the rest of the graph. This principle is underlying a new generation of graph clustering schemes that are commonly referred to as community detection. We use a method that is based on the concept of structure connectivity. Starting from the set of neighboring nodes of a node V on the graph and adding the node V to this set, we end up with a construct that we call the structure of node V. Based on the notion of structure, we can then define the measure of structural similarity between two nodes. We first consider the intersection between the structures of two nodes, and then normalize it by taking into account the cardinalities of these two structures. In essence, a high structural similarity value means that the two nodes are connected through many common neighbors, which indicates that they belong to the same cluster. Nodes A and B provide an example of nodes with high structural similarity value. On the other hand, when two nodes have a low structural similarity, this effectively means that they lie across an intercluster boundary. For instance, nodes C and A have a low structural similarity. Based on this observation, we cluster the graph by starting a walk process from a node and moving to neighboring nodes that have sufficiently high structural similarity with it. By recursively applying this process, we manage to extract clusters of nodes that are densely connected. The employed graph clustering scheme is very efficient for sparse graphs, since its complexity depends on the average node degree and the number of edges in the graph. Since for sparse graphs the average node degree is a small constant, the complexity of this scheme is linear to the size of the graph. In contrast, the complexity of k-means depends on four parameters, namely the number of iterations to convergence, the number of clusters, the number of nodes, and the number of dimensions of the node feature space. In practice, we noted that k-means was much slower in large datasets, since the number of clusters increases proportionately to the size of the dataset. Moreover, hierarchical agglomerative clustering scales even worse, since its complexity depends on the square of the number of nodes to be clustered. To make things worse, hierarchical agglomerative clustering requires n square units of memory to store the node dissimilarity metrics. The third step of our analysis framework pertains to the automatic classification of the extracted photoclusters into landmarks and events. In order to achieve this, we employ a simple feature description of each photocluster and then use standard classification techniques. We make use of two baseline cluster features and propose two new ones. The first of the two baseline features involves the duration of a photocluster, that is the time interval between its oldest and its newest photo. The second feature is defined as the ratio of the number of distinct users that contributed photos to the cluster over the number of photos they contributed. The basic premise of these features lies on the observation that events have a short duration and are captured by relatively few users, while landmarks are permanent and are photographed by many users. It is thus straightforward to draw a decision line separating these two classes on this two-dimensional feature space. However, there are numerous cases when this simple scheme fails. For instance, when a photo is mistakenly included in an event cluster, it may strongly affect its duration, thus leading to it being mistakenly classified as landmark. To this end, we propose the use of two additional features that make use of the tags accompanying the photos of a cluster. By exploiting the training samples, we can build two tag models, one for landmarks and one for events. Subsequently, we can compute the similarity between the tags of a cluster's photos with each of the two tag models and use the similarity values as the two additional features. Note that the described tag models largely depend on the language and the specific landmarks and events of a place. For that reason, new training is necessary for each place. The final analysis step is applied on the landmark clusters, which it improves in two ways. First, different clusters referring to the same landmark are merged. Second, a set of descriptive labels are automatically extracted from the individual photos in order to name the landmark clusters. The cluster merging step is based on the geodesic distance between clusters. A spatial proximity graph is constructed containing photo clusters as nodes and edges between them as long as their pairwise distances are lower than 200 meters. We apply the previously described graph clustering scheme on this graph and end up with metaclusters, that is, clusters of photoclusters. In this example, the four separate clusters referring to the same landmark, Park Güell, are merged into one. Finally, we make use of the tags accompanying the photos of landmark clusters in order to automatically extract descriptive names for these landmarks. We first filter out generic tags, that is, tags that are used frequently in the whole dataset. Then, we also filter tags that have low frequency in the particular cluster. In the end, we derive a set of tags that are characteristic of the particular landmark. We conducted a thorough evaluation of the presented framework. For our evaluation, we used the Flickr photo dataset comprising more than 200,000 photos coming from more than 7,000 users and described by almost 34,000 of unique tags. Our first goal was to compare the quality of the clusters produced by the graph-based clustering scheme against the one derived by the classic k-means algorithm. We conducted two kinds of evaluation. The first evaluation was based on a user study involving 20 people that explicitly assessed the quality of 20 clusters produced by the competing clustering schemes. The users were sequentially presented with clusters of photos without knowing the algorithm that produced them. Then they were asked to identify photos that they considered irrelevant with the rest of the cluster. Each photo cluster was evaluated by two independent users in order to quantify the extent of inter-annotator agreement. The second evaluation involved the implicit cluster quality evaluation by use of the geographical span of the clusters. For each cluster, we computed the average geodesic distance between members of the cluster and its center. Our underlying assumption is that clusters that have a large geographical span are more likely to contain irrelevant photos and are thus considered of lower quality. The results of the user study indicated that the graph-based clustering scheme produced clusters with significantly higher precision than the ones produced by the k-means. This result was confirmed for both visual and tag similarity graphs. Note that with the graph-based clustering, we could further improve performance by combining the visual and tag similarity graphs, while this was not possible with k-means since there is no commonly accepted method for combining different feature spaces. Another noteworthy observation pertains to the interannotator agreement that is expressed by the kappa statistic measurement. In the case of the graph-based clustering method, there was significantly higher agreement on the quality of the clusters than in the case of k-means. The large-scale evaluation by means of the geospatial cluster coherence further confirmed that the cluster produced by the graph-based clustering scheme are better localized and thus more likely to contain photos that are related to each other than to the ones produced by k-means. The difference is especially pronounced in the case of clustering by use of visual features. An additional evaluation we conducted aimed at quantifying the extent to which the two proposed cluster features are beneficial for the automatic classification of clusters into landmarks and events. We measured a significant classification performance improvement that ranged from 16 to 23% depending on the classifier used. Eyeballing several of the extracted landmark clusters along with their automatically produced labels further convinced us that the framework produces high-quality results. In addition, in terms of localization accuracy, the results were pretty impressive. In most cases, the landmarks were correctly localized with an accuracy of some tens of meters compared to their official location as provided by Wikipedia. Furthermore, looking into the event clusters produced by our scheme, we observed that a significant percentage of them is related to music events. Other important types of events with significant presence in the dataset were conferences, traditional events, and races. Moreover, a large number of events was associated with personal moments, for instance, going out with friends, and family occasions, such as weddings and births. In order to demonstrate the utility of the produced results, we developed a web application for browsing landmark and event clusters by means of a map interface. The resulting application is called ClustTour and is available online at clusstour.gr. We have so far included 10 European cities, but more cities are to be included soon. In this example, we decide to take a visit to the city of Barcelona. First, we get an overview of some of the landmarks and events that have been detected for this city. We then choose to see only the landmark-related clusters. It becomes obvious that there are two areas with a high density of landmarks. We zoom in and head for the hill of Montjuic. There, we run into the fountain of Montjuic and take a look at its pictures. Through the interface, it is easy to discover interesting spots that lie nearby. For instance, we discover a place with a panoramic view of the city, which also happens to feature the guns of Montjuic. Not far from there, we find out that AC/DC gave a concert in 2009 during their Black Ice tour. We may thus conclude that Montjuic hosts some pretty important rock concerts. Thank you for watching this presentation. We invite you to try out our demo at clusstour.gr and follow us on Twitter.